All right, time for a quick walkthrough of the linear regression learner by gradient descent. So the goal here is that we're going to try to fit a linear regression by gradient descent, and that'll give us practice with a lot of the basic building blocks of the FastAI toolchain, including PyTorch. So we've done this before. We started with the a notebook that did linear regression. So we had a bunch of data and we fit a line to it. Here we did a lot of manual code, and we took one little step in each direction and saw that the loss function went down a little bit. If we'd wanted to fit the entire thing by gradient descent, that's a lot of code. We got to write a loop to do that. And also this gets tedious to work when we've got more than one, or when we got models that are more complicated than just a single layer. So we'll introduce, or this notebook will introduce some ways of sort of a higher level of abstraction that will make this stuff work. So I'll just run a couple of our setup chunks here. Let me make sure that I am restarting the kernel so that everything is nicely clean here. And I will clear all outputs just in case. Okay, so first of all, we start with some utility functions. So whenever you see something in setup here in one of these notebooks, it should be something that's reasonably understandable to you, but skip it at first. Just run the cells and come back later to figure out how these things work if you want to. So here's where we're actually going to do. We're going to make a data set with a single feature, x, so one feature, and one continuous outcome variable, y. So what we've just done here is we've set a manual seed so that every time we generate this data, we get the same data set. We're going to keep regenerating and keep getting exactly the same data set, even though there's a random noise that's being added here. So this is a random number generator. I believe that noise is in the range of 0 to 1, and then we multiply by 0.5, so 0 to 0.5. So it's a uniformly distributed random noise. We've taken that noise and added it to some true predicted value here. So we took 500 randomly spaced x positions and just said each one of them we're going to multiply by 4, subtract 1. So this is like back in your high school fitting a line y equals mx plus b. Here's your m, the slope, and here's your b, intercept of -1. And then we have a uniform distributed noise. This is a pretty idealized situation. Most of the time, your data set will not be nearly this clean. We won't have nearly this many samples for a single one-dimensional problem. And we'll probably have more than one input dimension. But here we're using one input dimension so that we can clearly just plot it. Like x is on the x-axis and y is on the y-axis. I don't even label the axes because it just should be so conventional that this is the input and this is the output. I guess we could label it if we want. Plot that x label x and y label y. Sure. I'll semicolon at the end so we don't get that line here. Okay, so there's x and y. So x is the inputs. Sometimes we can call this the feature. So it's one feature. And y is the outputs, or the output of the model, or in this case, the target, what we're trying to predict. So let's fit a line to that. Just eyeballing it, looks like the line should go straight through the middle here. And of course, we're expecting that we get a slope of 4 and that our intercept should be -1. It does indeed look like when at x equals 0, y should be about -1, plus and minus. Okay. Oh, interesting. I forgot about this. Notice that the actual intercept is going to be a little bit higher than that. So I initially had the idea of making this a normally distributed random number, so that its mean would be 0. But in fact, what I ended up doing here is rand, not random normal. So noise has an average of 0.25. Well, it's as you'd expect because it's a number in the range 0 to 1. We're multiplying it by 0.5, so it's in the range of, so its average used to be 0.5. Now its average is half that, so 0.25. So our actual true bias is going to be -1, -1 plus 0.25, so -0.75. So that'll be what we expect the bias to be. That explains some things. Okay, good. I'm glad I noticed that. So anyway, let's fit a line to that. So previously we manually wrote out the y predictions. So we set up this formula where we said weights times x plus bias. And then we had to manually set up a way to do mean squared error loss as the predicted minus true, take that, square it, and compute the mean of those squares. And yeah, that's nice in that we're being explicit about what we're doing, but this can get complicated if our models get complicated. So in this notebook, we'll use the PyTorch's neural net.linear model or module as our model, and FastAI's learner class. There's a lot of stuff in FastAI, but I think that the learner is perhaps one of the more useful building blocks because it gives us a lot of functionality in a pretty reasonably simple, once you get your head around it, little unit. So we'll just start by running this. So we'll make some data loaders so that we can interface this data set with FastAI. So you don't have to worry about exactly how this code is made, except note that we're using a batch size of 5. And we're using that make data loaders function that I defined up here. So let's take a brief look at what one batch looks like. So we're going to take this data loaders. Note this has a train and also has a valid data loader. We'll take the train data loader and ask it for one batch. So let's look at that. I'll run batch here just to look at what that is. So we've got a tuple. Notice what's the type of batch? It's a tuple, and it's got two things in it. The first thing is the inputs, the x's. The second thing is the outputs, the y's. So we can say that our x batch is the first thing from the batch, and y batch is the second thing from the batch. So that our convention is to call the inputs to anything, to any model x, and the outputs from the model y. If you're writing this out in a paper or something, usually use y hat to mean the output from the model, and sometimes y true to mean the true values that you're trying to predict. But we'll just call it y for now. So this is the targets for this batch. So let's uncomment this here and use and look at what x batch is. So that's the first thing in the tuple. So this is a bunch of numbers. So here's a bunch of x values and then the corresponding y values. One little trick here, instead of doing batch 0 and batch 1, we could do a destructuring assignment. So this is where we're going to make a destructuring assignment here. So I'm going to do x batch and y batch on the left-hand side of an assignment statement. So this tells Python to basically line up the first thing, the thing at index 0 goes here into x batch. The second thing at index 1 goes there, and error if you got any more indices than that. So if we forgot y batch, then we'd get too many values to unpack. If we have, if we have y batch and we have an extra thing, not enough values to unpack. There, that's exactly the right values now. So x batch and y batch are the same. Now, what are these? Let's get a quick little view of this. So let me plot that data again. And I want to highlight that these points are particular samples from the other ones. So I'm going to take these and just plot them right on top. I'm going to take our x batch and y batch, and this may not work. Actually, it did. Okay, so it's okay with the dimensionality here. So here are 5 points from the original data set. So like here, 0.019 is this first one, maybe down there. And it looks like its y value is about -0.5, -0.6. Here, the corresponding y value was -0.616. Okay, so this one, the thing at index 2, was one of these points. So we found it. So here's 5 of them from this batch. I think if we ask for another batch, I told the data loader to shuffle the data. So I think it's going to give us a different batch this time. So let's run this again. Yep, it looks different. Now let's plot those points instead. Okay, they moved around a little bit. So basically every batch that we get is going to be a different subset of this data. So you can almost think of like these points are going to light up 5 points at a time. And then we're going to try to fit a line to fit those points, those 5 points just a little bit better. So that's the idea of gradient descent. So we've just set up the problem. And now in the next video, we're going to do a little bit on how this model works, how to define the model, and how to evaluate how good it is. So come right back.